Okay, so we have two more factors that we need to talk about when thinking about a molecule stability. The next factor is induction. You should be familiar with induction from Chem 1. We did talk about it when we were talking about NMR. If you remember when we talked about de-shielding a nuclei or de-shielding a proton and what that did to a peak in the proton NMR. We're going to use that same idea that an electronegative atom can create a very polar bond. Here, for example, this bond would be very polar, and that carbon would be very partial positive because of the inductive effect of an electronegative atom such as fluorine. So here are three molecules, and they're just carbon chains with the exception of the fact that this one has one fluorine, B has two fluorines, C has three fluorines. And so to answer the question, which molecule would have the strongest inductive effect? I think you probably know the answer, that more fluorines, more electronegative atoms, would give a stronger inductive effect. And reminder that the inductive effect is just that pulling of electron density towards itself or through the sigma bond system. So when we have fluorines and you're pulling, the fluorines are pulling electron density towards themselves and polarizing or really spreading charge throughout the molecule through the sigma bond system. So in an example such as this one, it looks very similar to the one we just saw where we have a molecule with one, molecule with two, or three fluorines on it. But this molecule, or these molecules here, have O minuses. So what we want to talk about is how does the inductive effect work to stabilize or destabilize these O minuses or a negative charge somewhere in the molecule? Well, the inductive effect helps distribute or kind of spread out negative charge. So when we, in molecule A, for example, the negative charge on the oxygen, that negative charge can help to be spread out towards the fluorine. When we have a negative charge in B and we have two fluorines, it helps to smear that negative charge out and distribute it throughout the molecule because the fluorines, of their inductive effect, they're pulling electron density towards themselves through the sigma bond framework. And like in C, we have three fluorines that are helping to spread and pull that negative charge towards them. So just a reminder that the more you can spread out a charge, the more delocalized a charge, the more stable that charge. So now when we look at this question, which molecule has the most stable negative charge? It's going to be C. The one with more fluorines is going to have a stronger inductive effect, and it's going to spread that negative charge out more. To explain why, we have to remember that the more spread out or delocalized a negative charge is, the more stable it can be. So now we know that more electronegative atoms creates more of an inductive effect. But what about where that electronegative atom is compared to the minus charge? So let's look here. Fluorine and the oxygen are on opposite ends of the molecule. Here the fluorine is on carbon 2, and so it's a little bit closer to the O minus charge. And in C, we see the fluorine is on carbon 4 with that negative oxygen on the next carbon over. So in C, the fluorine is closest to the O minus versus A where it's furthest away. And the question is asking us which molecule has, again, the most stable negative charge. Well, the closer the fluorine or the electronegative atom is to that negative charge, the more effectively it can help kind of distribute and smear this positive charge. So what we're going to see is that the closer an electronegative atom is to the localized charge, the more stable it will be, the more effective it can be with its inductive effect to stabilize charge. Okay, kind of think of it as like the closer the fluorine is to the negative charge, the more easily it can help to babysit that negative charge. And again, something that's more delocalized is going to be more stable. But I want you to think about this carefully. It's kind of confusing, right? We're saying that this example over here in orange is more stable because the fluorine is closer to the oxygen, so it can better distribute this electron density through the sigma bond framework. Over here on this side, the oxygen and the fluorine are on separate edges, and there's just a lot more distance between them. It's harder for the molecule in green to stabilize that negative charge. But wouldn't you think that having something negative so close to something else negative would cause some kind of repulsion or steric strain. It does not. We want to be really clear that the fluorine is not that it's a big negative charge that's causing steric strain with the O-. It is pulling electron density through that sigma framework up towards itself. And so that inductive effect is actually stabilizing rather than destabilizing. And finally, the type of electronegative atom can matter. So here we have 3 halogens, fluorine, chlorine, and bromine, all electronegative. And we do know that fluorine is the most electronegative. And we know that of these options, bromine is the least electronegative. Okay. The more electronegative the atom, the better it does at stabilizing charge through induction. So let's look at what the question specifically asking, which molecule has the most stable negative charge? The answer for that would be A, because fluorine is the most electronegative atom out of this series. The more electronegative the atom, the better it is at helping spread and pull and smear that negative charge through the molecule. It has a stronger pull because it's a more electronegative atom. And so from those examples, we have these main takeaways about the inductive effect. The first one being the more electronegative atoms there are, the stronger the inductive effect can be. We saw that 3 fluorines had stronger inductive effect than just 1. The closer an atom is to an electronegative atom, the more partial positive that atom will be, the more partial positive an atom will be. The closer it is to an electronegative atom, the more the inductive effect will make that atom partial positive that it's next to. The more electronegative an atom is, the stronger the inductive effect. We saw that fluorine has a stronger inductive effect than, say, chlorine or bromine. And the inductive effect is going to stabilize a negative charge in the molecule. That's what we saw in O-. Charge is more stabilized as a result of this inductive effect. So there's one more factor that we need to consider when thinking about the stability of an atom. So here we have 3 carbon atoms or molecules with different hybridizations. And here are those hybridizations written out. And what that means is that for an sp3 hybridized carbon, that really means that there are 4 orbitals doing the bonding, and they each have a composition of 25% S character and 75% P character. That trend follows for the rest of these hybridizations. So here are those different compositions written out. An sp3 hybridized orbital, there are 4 of them there, and each of them is about 1/4 S character and 3/4 P character. So remembering that a P orbital looks like this, kind of dumbbell shaped, and an S orbital is a circle. And so any electrons or anything living in an S orbital shape is going to be held closer to the nucleus because of the spherical shape of an S orbital. And so when we look at all the composition of these different orbitals, when we get all the way down here to an sp hybridized orbital, there are 2 of them, and it is half S character. So an sp hybridized orbital is going to be holding the electrons much closer to the nucleus because of the spherical shape of that S orbital. And so the main takeaways about orbital hybridization in terms of stability is that an S orbital, because it is closer to the nucleus, just because of its shape, is actually going to be much lower in energy. Electrons living in that spherical shape are closer to the nucleus and therefore more stable and lower in energy. And what we saw on the previous slide is that when we have hybridized orbitals, like an sp hybridized orbital, the greater percent S character, that means that the alone pair living in that orbital, or the electrons living in that orbital, can be much closer to the nucleus, and that makes that orbital and the electrons living in that orbital much more stable or much lower in energy. We will work on applying this as we see more examples of acid-base chemistry later on.